Up to this point in the course, when we're talking about calculating electric fields using Gauss's law, we've actually technically been talking about insulators. And with an insulator, you can have a situation where the charge is distributed not only on the surface, but within the actual solid material that makes up the charged body. So this is why I can talk about specifically just a line of charge rather than having to specify that it's actually a wire or something like that. And this matters because each particle that is making up the object exerts an electric field, and it can exert electric field on every other particle that makes up the item. So if you have this sort of net distribution of electric fields, you're going to get motion of the charges. But with an insulator, we don't worry about that because the charge doesn't flow very easily. So we can have a situation where the particles or charges are sitting still, electrostatic situation, in an insulator, whether there's charge just on the surface or whether there is charge inside of the object. On the other hand, with a conductor, the charge can flow very easily. And so what ends up happening is with conductors, the charge is distributed on the exterior of the item. So if you have a sphere of charge with a conductor, there is no net charge inside of that sphere, and all of the excess charge is distributed on the outside. So when you set up that situation, that charge is going to naturally flow until you get sort of an even distribution. And the electric field inside of the actual physical object that is the conductor is zero. This means if we apply Gauss's law, so I have Gauss's law written here. Once again, we're not worried about the electric flux, we're trying to find the electric field. So I've drawn in blue here my Gaussian pillbox. And because the electric field is zero inside of the physical object that makes up the conductor, there's no field lines coming from this direction like there would be for an insulator. There's just field lines coming off of the surface. That means that changes what dA is, because instead of being 2A, it's now a single A, because we're only worried about what's coming up off of the surface. And we don't have anything coming, any field lines coming from the inside of the physical object. All right, so in the next part of this video, we're going to look at the concept of what happens whenever we add an external charge and how that leads to the charge being redistributed on the surface of the conducting object. All right, so in the situation here, we have a conducting shell. And this is a spherical shell, so I can't draw the three-dimensional shell or else you wouldn't be able to see inside. But you have to remember this is a three-dimensional sphere, and this is conducting material. And this conducting shell already had on its surface, whether it's distributed on the inner part of the shell or on the outer part of the shell, a net charge of negative 3Q. So that could mean there was negative 1 here and negative 2 on the outside, but it's on the surface somewhere, not inside of the shell. We then introduce inside of the conducting shell a charge of 2Q, and that's going to cause temporarily the charges to move around until they're distributed once again in such a way that if I were to draw a Gaussian surface that went through the conducting shell, remember inside of the conducting shell you have to have an electric field that is zero once everything settles out. So we have to see that the charge is going to distribute itself in such a way that when I do apply Gauss's law, that E is going to equal 0 inside. All right, so remember when we're looking at Gauss's law, we're talking about the integral of E dot dA is equal to Q enclosed divided by epsilon naught. So this means that if my Q enclosed is 0, my electric field is going to be 0. So I'm going to draw my Gaussian surface, so do that in green, so Gaussian surface in such a way that it goes through the conducting shell, and so the charge inside, enclosed, has to be 0. So if I have 2Q as my charge sitting there inside of the empty cavity, that means to balance that out, I need a negative 2Q. So that means there's going to be a negative 2Q on the distributed around in some fashion on the inside surface of that spherical shell. So we're going to have a negative 2q here. Now we know the conducting shell originally had a net charge of negative 3q. So if my total is 3q and I have a negative 2q on the inner surface, that means whatever is on the outer surface has to add to that in such a way to get that negative 3q. So negative 3 plus 2q, so to add it to the other side to solve for x is going to equal negative 1q. So that means distributed along the outer part of the shell is going to be a negative 1q.